Let's talk now about a specific example of finite MDP in which we can analyze each of the elements that we have been talking about. This is the recycling robot problem. Imagine that you will program a robot that will move around a university campus, for example, and the goal of the robot will be to recollect as much cans, soda cans as it can. So at each step, the robot has to decide whether it should actively search for a can, if it wants to wait for some can to bring it, someone to bring a can, or it should go home base and recharge the battery. So this agent would have three possible actions: search for a can, wait for a can, or go home and recharge. Searching is better, but runs down the battery. If it runs out of power while searching, it has to be rescued, which is bad. So we don't want that. And the decisions made on basis of current energy are based on the current energy. So the state will be in terms of the battery, the level of the energy of the battery. So it could be battery high or battery low. And the rewards are going to be the number of cans collected. So this is a very simple problem, but it contains all the elements of a finite MDP. So here in this graph we have the two states that the agent can find, like battery high and battery low. And well, this is defined here as a set. So the set of states is going to be high and low. It will have a set of actions defined for the state high of battery. So when the battery is high, the agent can search, or it can wait. And when the battery is low, it has also an extra action, which is recharge. So if the agent has high battery, if the robot has high battery, it can perform the action wait, or it can perform the action search. If the agent decides to perform the action wait, with probability 1, will stay with a high battery, and it will receive a reward, some reward that and some expected reward given that it is waiting. Okay, so R wait will be the expected number of cans while waiting, and R search will be the expected number of cans while searching, where, as we said, we will assume that the number of cans that it can get while searching is larger than the number of cans that it expects to gain while it is waiting. So if the battery is high and performs search, then it could happen two things. With some probability alpha, the agent will stay in with high battery and receive a reward expected by searching, or with some probability 1 minus alpha will transition to a low battery state, again with the same reward by that it would receive by searching. Now, if the agent is in state low, it could perform three actions. If it performs search, with some probability beta, will remain with low battery and gain the reward by searching. If the action performed is search, can also with some probability 1 minus beta will transition to probability to state high, but obtain a reward of -3. So how is it possible to go from low to high? What we are saying here is that the robot, while it is searching, it will lost all the energy, and it will need to be rescued by a person. So in the end, the robot will recharge the battery, will have a high battery, but it will receive a punishment of -3 because it needed to be rescued. If in low battery it performs a wait, with some probability 1 will remain in the same state, low, obtaining some reward, R wait. And if the agent performs the action recharge, it will move to state high with probability 1, but it will receive zero reward. So recharging has no reward. So here you can see all the elements. If our reinforcement learning problem were as easy as this one, then you can even make a graph of this kind. But usually the problems that we need to solve with reinforcement learning are so challenging that you cannot. The number of states or actions or both are very large. But this exercise, this example, is very good for understanding each of the elements of a reinforcement learning problem. So we need to talk about value functions. Most of the reinforcement learning algorithms are based on estimation of value functions. The value functions are functions that will store the value of each of the states. So the value of a state is the expected return starting from that state. So the value of a state will contain how much reward you expect the agent to gain if the agent is in that state, and it depends on the policy. That's why in the definition we always have a pi, because it means the amount of returns that you will get from that state while following a specific policy. So this is the definition of a state value function for some policy pi. So the v of some state, the value of some state while the agent is following a policy pi, will be the expected amount of return that the agent will receive while it is in state s in time step t, and the agent keeps following the policy pi to select the next state to move into. So we can rewrite this in the way we defined the return in the previous slides, like the discounted sum of the rewards from k equals 0 to infinity given the current state s. The value of taking an action in a state under policy pi is the expected return starting from that state, taking that action, and thereafter following pi. So in the same way that we can define a value function for states, a state value function, we can also define action value function. In this function we also include, or we also add the action. So we say the q value of this pair of state and action, and all you need to consider is the return. In the same way that in the state value function here you will consider the current state, but also in this case you will consider that the action that you are performing in that state is action A. So it's very similar to the definition of the value state. So this is the action value state. We usually refer to that as q, the q values, and v values as the state value. There is a very important equation in reinforcement learning that is called the Bellman equation, and we define the Bellman equation for a policy pi as this, So we will see how we can come to this definition. First, remember that the return is defined as the discounted sum of rewards that you will get starting from the current state t. So we can write it as this. But then if we factorize this gamma here, we can say gamma times and all this expression here. But this expression here will be simply defined as the return starting in time step t plus 1. So we can summarize this as the reward in time step t plus 1 plus gamma of the return starting in time step t plus 1. And this is what they have done here. Okay, and we were simply saying the value of some state s will be the expected reward that it will get in the next time step plus gamma of the value of the next state starting in the next state in time step t plus 1. And this is I mean, here we are defining this value of a state as an expectation, but if we want to compute this explicitly as a probability, then we need to consider also the probability of selecting one action given the current state, and this is for every possible action in the action set, and also the probability of transitioning from one state to another after executing an action A, where this S prime makes reference to any possible state in the state set. And finally, we can write the reward that you will get from going from S to S prime by executing action A, which will be this reward here in the reward in the next time step, plus gamma of the value of the next state. And this is what we call the Bellman equation. This Bellman equation is a system of equations, and you will have an equation for each of the states of your problem. If your problem have 10 states, then you will have 10 equations. If your problem has an infinite number of states, then you will have an infinite number of equations. It is important to notice that the definition of this equation is a recursive definition. So to compute the value of some state S, you need to access the value of all the possible next states. So it calls itself with a different parameter. Here we can see some diagrams. This is a diagram, on the left is a diagram to represent the computation of the value function. So we have a state in this white circle, and then we have some possible actions to be performed. So each of these branches of the tree represent a possible action. If you select an action, some action A, then that will give you a reward and a possible next state. So after performing an action, you can follow or transition to different states if we consider that this is a very stochastic problem. So this diagram will represent the amounts or numbers that you need to have in order to compute the value for a state. Okay. On the right we have a diagram, but this is for computing action values. So in the action values we have also an action. So we start by considering the action that was already selected, and after executing an action we can have possible next states represented by these two white circles. And after you know the next state, you can access to the next best action, or the action that you can execute after transitioning to the next state. So this diagram will represent the information that you need to calculate the value for a pair of states and actions. Imagine a problem that is a grid world, in a grid world of 5 by 5 squares, in which the actions are 4 going north, south, east or west. So we have only 4 actions in this small grid world. Let's assume that the task is deterministic. So by deterministic we mean that if we are in some state and we perform action going right, going east, it is with probability 1 that you will transition to the square that is to the right. If you are in a square and you apply action go north, with probability 1 you will end up in the square that is above the previous state. So this is a deterministic task. It's not an stochastic task. If the action will take the agent off the grid, no move will happen in reality, but it will get a reward of -1. So we are talking about, for example, suppose that you are in this square and the agent perform actions. The action go right. The action go right would move the agent off the grid. But in this exercise we will assume that the agent will remain in that. It's like if there were a wall here and the agent just get the wall and remain in the same state, but it will receive a reward of -1 because that's not good. That's not a good action. Other actions produce reward 0. So every movement will receive a reward 0, except when you move into a wall and when you go out of states A and B. So if the agent manages to get into state A and then applies action go west, the agent will leave the state A, will receive a reward of +10, and it will be moved automatically to the state A prime, which is this one here. Something similar will happen if the agent is in state B and moves outside B. It will receive automatically a reward of +5, and it will be moved to the state B prime. So this is a very specific experiment with this small world, and if you implement the Bellman equation to calculate the values of each of the states with some gamma 0.9, the values that the algorithm will learn are these ones here. And if you notice, you will see that the state A has the largest value, is the most important state with a value of 8.8, and the second most important state will be state B with a value of 5.3, and this has been learned from estimating the Bellman equation, by estimating the value function for each of the states using this formula here. Okay. So this is the general idea behind reinforcement learning, to discover which states are more important in order to maximize the amount of reward. Let's talk now about optimal value functions. For finite MDPs, for finite Markov decision processes, policies can be partially ordered. By partially ordered, we mean that, for example, policy pi, we will say that this is larger or equal to policy pi prime if and only if the value for all the states S following policy pi are larger or equal to the values of the same state S while following policy pi prime. Okay, and this should be true for every state in the set of states. So given two policies, if this is true, the value of some policy is larger or equal to the values of the other policy, we say that this policy will be better than the policy pi prime. There is always at least one, but there could be many policies that are better or equal to all the others. This is when you find this policy, you have found the optimal policy. We denote them all by pi star. Optimal policies share the same optimal state value function. So even though there could be many policies, many ways to behave, all of them should have the same value function, the same optimal value function. And the optimal value function, which is V star, is the value function that maximizes the values for all the states. Optimal policies also share the same optimal action value function. So this is also true for action functions, action value functions. So when we talk about Q star, we're talking about that specific Q value function, Q action value function that is maximum for every combination of state and action. This is the expected return for taking action A in state S and thereafter following an optimal policy. So we can define the Bellman Optimality Equation for V star. The value of a state under a policy, optimal policy, must equal the expected return for the best action from that state. So if we have some optimal value function, we can define the equivalent optimal action value function, and to do that we simply need to maximize the Q function by checking all the possible actions and selecting the action that maximizes the Q value. So as we defined before, the Q value of a pair of state and action is given by the expected return, the expected reward that you will get in the next time step, plus the discounted, the gamma of the value of the next, starting in the next time step, t plus 1, given the state and the action defined up here. And well, we can represent this with these backup diagrams that we saw before as the value function, the value diagram, remember, starting in this state but with a maximum over the possible actions. This is representing a system of nonlinear equations when we want to maximize over the possible policies and possible states and actions, and the solution of this is the optimal value function. You can define it also in terms of the action value function. What is the optimal Q function? In this way the backup diagram will look like this. So you will have a state and action. You will consider all the possible transitions, but once you have considered the possible transitions, you need to compute a maximum over the possible next actions, possible next A primes. Again, the solution of this system of nonlinear equations will be the optimal action value function. Any policy that is greedy with respect to the value, the optimal value function, is an optimal policy. So if given a value function, like for example this one, if we consider this value function to be the optimal value for a specific problem like the Gridworld, then if you always select the next state to move to as the state with the largest value, then you are behaving greedily with respect to that value function. And if this value function is the optimal one, then the policy is also an optimal policy. So for example, take this state here. If you go left you will have a 13 value. If you go up, you also get the same number, 13. So the policy here could be going up or going left. But if you are here, for example, if you go up, you will get 22, which is the largest value that you can get compared to 17.8 going left and right, or 17.8 if you go down. So here the best policy would be to go up, and that's why it is written here going up. So this policy is an optimal policy because it is derived from the optimal value function. So what about optimal action value functions? Given Q star, the agent does not even have to do a one step ahead search. So let me go back here. If you are working with value functions, if you are estimating value functions, once you have estimated this, you need to look ahead. What are the possibilities that you have, and then you need to select the state with the largest value, like in this case this 22. Okay, you need to look ahead one movement. But if you are working with action value functions like the Q function, then you don't need to look ahead because the policy will already have stored what is the action that is the maximum, that is the action that is maximizing the next Q value. So that's why for contour problems it is better to work with action value functions than using state value functions. Sometimes having state value functions is not enough. It's not possible to solve your problem. Imagine, for example, that you are programming a robot, a humanoid robot, and the robot needs to walk. Maybe if you work with a value function of the environment, you can know where is the best next position where you want the robot to walk. But knowing where you want your robot to go to is not the same as knowing how much the voltages should change in order to make the robot move really and get to that state that you want. So in those kind of problems, you better learn what is the best action to perform based on the current state, and not only what are the next states that you would like your robot to visit. So solving the Bellman Optimality Equation. Finding an optimal policy by solving the Bellman Optimality Equation requires the following: accurate knowledge of the environment dynamics. So we will see in the next chapter how we can solve these Bellman equations if we have the model of the environment. So if you want to solve it completely perfectly, you will need to have this model of the environment, these dynamics. If not, you can only expect to approximate the solution. Also, to solve this problem, we have enough space and time to do the computation, especially if we are talking about large state spaces and large action spaces. You will need a lot of space and time, a lot of memory, and also you need to have a Markov property in the environment. Remember, all these algorithms that we are going to see are based on the assumption that your environment is Markov. Now, many of the problems that are solved using reinforcement learning are not strictly Markov. But in many of these problems, even though it is not completely a Markovian property there, you can apply these algorithms and get good results. Okay. How much space and time do we need? Okay, so the number of states that you will need will be polynomial via dynamic programming methods. So this is polynomial in terms of the number of states. However, this number of states is usually huge. Like in the example of the backgammon system, the TD backgammon, that system, that problem has 10 to the 20 states, so it's very large. So if you need to work with a problem with a very large state space like this one, you won't be able to learn the value for each single state. So you need to approximate these values, because maybe you can visit only a very small percentage of these states, and the value of the other states, you will need to approximate these values. You will need to predict what will be the values for all those states that you cannot visit during the training, because you cannot simply train forever. You need a certain number of time or interactions to learn. So for this kind of problem, we will need a way to approximate these value functions or these action value functions. And currently the best way to do that is using a deep neural network. So you can use a deep neural network to store the values of all the states in your environment. So many of the reinforcement learning methods that are nowadays applied are understood as approximately solving the Bellman Optimality Equation, because, as I said, you will need to approximate somehow the values of the states or the value of action and states. So in summary, from this chapter you should be able to understand very well what are the states in a problem, in a reinforcement learning problem, what are the actions, how the rewards can be defined. You should also understand what is a policy, this function that will let you know what is the best action to be selected. In this case, we have defined that policy as a stochastic function. Okay, and also you need to understand very well the concept of return, which is basically the expected rewards, the expected sum of reward that you will get starting in some state and executing actions given by some specific policy. You should also be able to understand the difference between episodic and continuing tasks, the concept of Markov property. In terms of the Markov decision process, you should also consider, or you should also understand the transition probabilities, which is the model, the probability that you will go from one state S to some state S prime by executing some action A. Also the concept of expected rewards, which is basically defined as the discounted sum or the sum of discounted rewards. In the case of the value functions, we talked about the state value functions for a given policy and also the action value function for a given policy. So this is the V function and this is the Q function. And for both functions, we saw the definition of the optimal state value function and the optimal action value function. So we also talk about the optimal policy, which given an optimal value function is the policy derived from selecting the best actions, the best actions or the best states based on these values that we have estimated. And to solve an MDP, we apply the Bellman equations. And with more challenging problems, we cannot calculate or solve this explicitly, so we approximate the solution. And in that situation, we usually need a function to approximate the value state or the state value or the action value functions. And these approximators are usually deep neural networks. Okay, so I hope this is this is useful for understanding the basics of the MDP problems. In the next presentation, we will talk about dynamic programming algorithms, which are the basic way to solve MDPs. And then we will talk about Monte Carlo methods. And finally, we will talk about temporal difference methods, which are basically the best of dynamic programming and the best of Monte Carlo. Okay, so thank you and talk to you later. Bye.